Thank you, everyone. I'm very excited to be here. I love talking to normal people about what we do at the university, because as a theoretical physicist, we're just basically sitting in front of the computer thinking about stuff for a good 10 hours a day. This is like the highlight of my day. Okay, so I want to talk about a research project that I'm working on right now. So this is really like at the edge of science. But this is my theory, so it might not be proven. To tell you about matter-antimatter asymmetry, or the dark origins of it, I will first have to tell you what matter is, then what antimatter is, what I mean by the dark origin of matter-antimatter asymmetry, and then I tell you what is this asymmetry, where did it come from? Okay, so starting with matter, what is it? It's basically everything we see. And it goes from very, very huge scales of galaxies to the very small scales of atoms and molecules. And I'm hoping that you remember from your high school education that what physicists or philosophers thought of the universe and the fundamental building blocks of it as air and water and whatever else it was, is not a correct scientific picture of nature. Scientists have been able to break things into very, very small pieces to see that everything is actually made of very small things like atoms and molecules. And you probably remember the periodic table from your chemistry classes, I guess, where they told us, this is it, everything we have in nature is made of this stuff. So that picture has changed a little bit. What scientists have done is that they've managed to break molecules into atoms and then atoms to smaller pieces. But before we go to the smaller pieces, let me give you a feeling of the size of things. For example, if you have a classroom of the order of 10 meters, then an atom would be 10 to minus 15, or a millionth of a millionth of a millionth of a meter. Something like that. So very, very small scales. As I said, scientists have been able to build very, very high energetic colliders to break particles into pieces. And they found out that atom is not the building block of everything. Inside an atom, you have a proton with an electron, let's say, going around it. The electron turns out to be a fundamental particle, meaning that we haven't been able to break it into anything smaller. But the nucleus, which has protons and neutrons, is not a fundamental particle. The nucleus itself, with the protons and neutrons, they aren't fundamental particles either, and we've been able to break them down into smaller pieces or smaller particles called quarks. This is a technicality. We're physicists, we're not very imaginative. We come up with random names like up and down quarks, which is what protons and neutrons are made of. So that's basically what matter is. And we've come up with our own, I can't call it a periodic table, we call it the standard model of particle physics. And these are all the particles that there are in nature. And I don't mean just on Earth. Everywhere you look, this is what you see. At the center of this beautiful graph is the Higgs boson, which was the particle that was discovered at the LHC a few years ago. Okay, so that's matter. Let me tell you about antimatter. I'm sure you've heard of it if you've seen, what's it called? Angels and Demons, the movie. They talk about antimatter and how dangerous it is. Let me tell you a little bit about what it is, then we talk about the dangers of it. So you all know the electron, which is a negatively charged particle. It's a fundamental particle. All the atoms that you see around them, around us, they have electrons. For every particle that we have in nature, every matter particle, there is an antiparticle. The antiparticle of electron is called a positron. It has exactly the same properties as the electron, the same mass, but it has an opposite charge and it moves differently. So you can call it the mirror image of an electron. So if there is an antiparticle for every particle, that means that we could also have anti-atoms, and we do. So if you've got exactly the same mechanism as you have in a, let's say, matter atom with protons and electrons, you could have an antimatter particle, like anti-hydrogen, as it's shown in this picture, with an antiproton in the center and an anti-electron or a positron going around it. So basically, we know that every matter particle has an antiparticle mirror image. So the picture that I showed you of the beautiful standard model of particle physics, we know already there is a mirror image of all of those particles. So we know they exist, we can produce them in experiments. It takes a huge amount of energy, but let me tell you later what happens when we do produce them. So having talked about matter and antimatter, I want to tell you very briefly what the dark world is, or what dark matter is. It's basically matter that we don't see. So we look out into the sky, we see galaxies and stars move in certain ways, but if we assume the content of a galaxy to be only what we see, it doesn't agree with the way it moves. So scientists have kind of come up with the idea of a matter that is there, which means that it kind of interacts gravitationally with the visible matter. So it does have an effect on how galaxies and stars rotate, but we don't see it. So we call it dark matter. And we know there is a huge amount of it, actually 5 times more than the amount of matter there is in the universe. There is dark matter, but we have no idea what it is. We have no idea if it has a smaller structure. Is there a, let's say, dark model with lots of different dark particles? We don't know. But as theorists, our job is to come up with theories that have an explanation for dark matter, and then we hope that our experimental friends would find those particles and get us a Nobel Prize. So the models that I'm working on, they usually have brothers and sisters of the Higgs boson at the center of the dark world. Okay, so we've talked about matter, antimatter, and what is the dark world. Let me now connect them together. We know that at the very beginning of the universe, about a second after the Big Bang, matter and antimatter were produced equally. The laws of nature that we have treat matter and antimatter mostly equally. So if matter was being produced, antimatter was produced exactly the same amount. But somehow, we don't know why, we don't know what this process is, but there was a process that produced a little bit more matter than antimatter. Because the reason we think that is we look out into the world, and all we see is matter. Every galaxy we see, everywhere we look, all we see is matter. And the reason that we know we're not seeing any antimatter present is because when matter and antimatter come together, they annihilate. That's a fancy word we use, and by that we mean that they come together and they just disappear, but produce a huge amount of energy. So if there was a matter-antimatter interaction somewhere out in the universe, we would see, let's say, energetic photons coming out of it. So it would be sudden bright spots in the sky, just appearing out of nowhere. And we don't see that. We look outside into the universe, and everything we see is made of the matter that we already have on our planet. So, but there is, so as I mentioned, we look outside and we only see matter, even though we know right after the beginning of the universe, matter and antimatter were produced equally. So this is what we call the asymmetry. We don't know why, but there's more matter than antimatter. The theories that I work on are basically hypothesizing that this mechanism that produced more matter must have happened in the dark sector. We don't know anything about the dark sector, but what I'm working on is theories that would give you dark matter from the dark sector, but also have this mechanism that would produce an excess of matter, which would lead to an excess of the visible matter that we see, which then explain the matter-antimatter asymmetry in the universe. And that's my last slide. Thank you so much for your attention.
Thank you, Vignis. This all is so exciting. I must say, my mind boggles at this stuff. But let's try and get some more answers to this. Okay, matter-antimatter, super fascinating. How can we actually be sure that there is more matter than antimatter? You already went into this at some length, but convince us.
So I guess the question would be, how do you know the next galaxy is not made of antimatter? Something like that. But as I mentioned, matter and antimatter, when they come close to each other, they annihilate into energy. So if there was, let's say, if I produced a bit of antimatter right here on this stage, it will annihilate with the matter around it right away. So by just looking out in the sky and not seeing any energetic photons coming out of no source that we already know, we've come to the conclusion that there's no antimatter around us, and everything seems to be playing with the rules that we already know. And by the rules, I mean the physics laws that we've come up with for the matter universe on our planet. And it seems everywhere we look, it's the same laws, it's the same properties, it's the same kind of stuff.
Well, we'll just have to try and understand that as well. When we talked earlier, you said something super interesting about how can we actually know what if we are living in a world of antimatter instead of matter?
Yeah.
How could we know?
That's a very good question, yeah. So if we were actually living in a world that had no matter and only antimatter, it would look exactly the same. And it's basically just a definition. We've evolved on this planet, we've called what we see around us matter, and what the stuff that has exactly the opposite properties, like the electric charge, we call antimatter. So we know everything around us is made of one type of matter. If you want to call it antimatter, it doesn't make any difference. You could just say the whole universe is made of antimatter, we don't see any matter. It's the same story.
It's so interesting how physics can collide with semantics and language even. That's very fascinating. Can we produce antimatter?
Sure, yeah.
How would we do it?
So at CERN, for example, the Large Hadron Collider, they do produce antimatter. As I said, what happened in the beginning of the universe, when there was a lot of energy around, all of those processes, they produce matter and antimatter in equal amounts. That's exactly what happens on Earth in our particle colliders as well. We can produce antimatter, but they do annihilate with matter particles right away. They have we can't keep them for long. If you want to keep them, you have to go to some extent of, you have to have a lot of energy to be able to separate them from matter. Otherwise, as soon as you produce them, they annihilate away. Yeah.
So, delicate things.
Yeah.
Interesting. Okay, you said that, okay, your days as a theoretical physicist consist of looking at the computer. Can you tell me a bit about how theoretical and practical physicists collaborate?
Yeah, so this is kind of like what Laura was saying about people who work on our galaxy and stuff outside of our galaxy. That's the same with theoretical physicists and experimental physicists. We are all aware that we need to be talking to each other more, but we don't, because we feel like they know so much more, they think we know so much more, and we don't even understand each other very well. We don't go to each other's conferences. So yeah, that's a bit of a sad story. But we do have another type of physicist which is called a phenomenologist. That's the guy who understands our language and the experimental physicist. So we both try to talk to phenomenologists or write papers with them, because then I come up with the theory. With the phenomenologist, I will figure out what would be the experimental signature of my model. Then he goes and talks to the experimental physicist. They come up with a way of looking for that particular signature. And if they find it, we all win a Nobel Prize, which is fantastic.
Sounds like something we should be aiming at. Last but not least, I really want to hear how you ended up as a physicist. Why physics? How did you become a researcher?
Yeah, I think as a kid I was always really interested in breaking things into little pieces to see what's inside them. And I think I have to get the credit to Albert Einstein. I've always, even as a kid, when I kind of read the, let's say, simplified version of his theories, I thought it was absolutely amazing. And the more I learn, the more amazing I think he is. It's just, I always wanted to really understand what he does. I wanted to be like him. I would say curiosity and Albert Einstein. Those are the two reasons I became a physicist.
We are really happy that you did, because your work sounds fascinating.
Thank you,
I think now we need to move forward, but let's give a huge round of applause for Viginės.
Thank you very much.